All right, so let's quickly go over this idea of chemical equivalence. Basically, this is trying to show you, as we did with the periodic table, that every element, a mole of one element, doesn't have the same mass as a mole of another. So, what if it's a partial mole? So, that's what we're going to do here. So, sulfur, if you have 16 grams of sulfur, you want to convert that to moles. And if you go to the periodic table, sulfur is 32.06, or basically 32.1 grams in 1 mole of sulfur. And then when you divide 16 by 32, you get about 0.5, right? So let's just call it 0.5 because that'll save me time. So 16 grams is half a mole of sulfur. Well, how many grams is half a mole of carbon, which is the other thing it's asking here. So, right, what's the grams of carbon? So you're going to do zero point 0.5 moles. And now you know for every 1 mole of carbon, there's 12 grams. And so that'll be 6 grams of carbon. So 16 grams of sulfur is the molar equivalent of 6 grams of carbon. So I usually call these molar, and in fact, that's what people in industry call them, but they're calling them chemical. So be aware. So for this one, we have 50 grams of strontium. So we got to convert that to moles. And on the periodic table, strontium, which is number 38, is 87.62 grams in 1 mole. So then you figure out how many moles of strontium that is. And 50 divided by 87.62, 0.570. And then you convert that moles back to grams of arsenic in this case. And arsenic, which is number 33, is 74.9 grams. So 0.57 times 74.9 is 42.7 grams. So if you have 50 grams of strontium, it's the equivalent of 42.7 grams of arsenic. Ta-da! All right. Then we talked about percent. And if you were told to figure out the percent of these that are green, right, you would want to count the total and then divide by the green. Hopefully that makes sense, right? So here are the green ones. So the percent of those is the total the amount of green divided by the total. So I would add up everything, and then and then I should have just muted instead of mugging my microphone. Anyway, and then the green is the 174 on the bottom, right? And the 27 on top. Spoiler alert, there's the answer. So 27 divided by 174 is 15.5. So it's actually 0.155, which hopefully you know is 15.5 in a percentage, right? So, and the percent purple would be because there's 20, 11.5, and the percent yellow would be 27, and all the percentages would equal 100 when added together. So let's do this for the elements, which I'm so lazy I just left it on here because it's pretty straightforward, I think. Carbon, you have 3 carbons. We do our little chart, right? So we're going to do our little chart like we've done. And 3 carbons, each one has a mass of 12, so that's 36. 8 hydrogens, each one has a mass of 1, so that's 8. You add them up, it's 44. So the percent carbon is the 36. The amount carbon contributes to that 44. And the percent hydrogen is the 8 divided by 44. And you get 18.2. I'm not sure what's going on there, but 18.2%. And then if you add 18.2 plus 81.8, that's a plus sign. You get 100%. So percent sodium, sulfur, and oxygen and sodium sulfate. So there's 2 sodiums, each one weighs 23 on the periodic table. There's 1 sulfur, each one weighs 32.1, and there's 4 oxygens, and each one weighs 16. So then you add all that up. The total is 142. The percent sodium is the 46. The amount of sodium contributed to that total, 142, which equals 0.324, which is 32.4%. Sulfur would be the amount sulfur contributed divided by the total, 142. So that's 0.226 or 22.6%. And the percent oxygen is that 64 divided by 142. So 0.45 or 45%. And again, if you add all those up, you would get 100% because each thing. So that's like a trick question they like to throw in there is like if the rest is sodium. Oh, we'll see that later anyway. All right. How many grams? So this goes back to what we were doing before. This is asking for how many grams of carbon are there to get, or how many grams of sucrose do you need to get 50 grams of carbon? So how many grams of this giant thing do we need to get 50 grams of carbon? So this is a two-step process. You have a problem like this, figure out your percent carbon, and then you're going to set up an equation where 50 grams equals the percent carbon times whatever mass of the total it is you need. Because that's what it's asking, right? How many grams of this stuff? So how many grams of this stuff times the percent of carbon will give you 50 grams, because that's what it'll give you, 50 grams. So it's going to be a larger number than 50 grams because this isn't 100% carbon. It's only like, well, it turns out to be 42% carbon. So step one, figure out your percent carbon. So you got your atoms. There's 12 carbon atoms. Each one has a mass of 12, so that's 144. There's 22 hydrogen atoms. On the periodic table, there's 1 gram per mole of hydrogen, so that's 22 grams from hydrogen. And then there's 11 atoms of oxygen. 16 is the mass for every oxygen for 176. You add all those up, you get 342. So your percent carbon is the 144 divided by the 342, so it's 42.1%. So that's step one, the percent carbon. Step two is to put it in this equation. 50 grams equals the percent we just found, 0.421, times some mass that we're trying to find. How many grams of that stuff? So then what we did there is we had basically 50 grams equals 0.421x, divide both sides by 0.421, and you need 118.7 grams of sucrose to have a 50 gram sample of carbon. So if you needed 50 grams of carbon for some reason, you would need 118.7 grams of sucrose and then figure a way to get that carbon out of there, maybe by burning it into carbon dioxide or whatever. But then it's still not carbon, it's carbon dioxide. All right. There you go. So, and then we talked real quick about how the essential amino acids, if you take the average of the nitrogens in here, so here's a nitrogen in valine, there's one in leucine, there's one in isoleucine, there's one in phenylalanine, but then these other ones have multiple. So this has 3, arginine has 3 nitrogens, lysine has 2 nitrogens. So if you figure out the percent nitrogen of all these, it comes out to about 16%. And what they used to do in the old days was just take dog food and see if it had 16% nitrogen in it, because that was a cheap um, test to run. But one company figured out, well, if they use things without nitrogen, like sawdust and husks of grains that nobody uses, like wheat husk and corn husks and whatnot, they could throw in there melamine, which has a lot of nitrogen. And then when you did this test for how much percent nitrogen you'd have 16%, even though none of it was an amino acid. So this 16% nitrogen test assumed that no one would want to put anything but an amino acid in there. And this company decided, well, we're not going to put any amino acids in there. Let's see what happens. So, yeah. And then a lot of dogs got sick. And I was wondering at the time, why would you put melamine? Like, what was the idea? And the idea behind it was they were trying to boost their nitrogen in their dog food. So they were using melamine. They didn't, I don't think at the time, knew it would make dogs sick. Obviously, they didn't care to look, but I don't think they did that. But anyway, all right. Then we got into hydrates, and hydrates are ionic salts. Sometimes they contain water, and I put a lot of time into this lovely picture. to let you know that sometimes salts hold water, like sodium sulfate. And they're written in the format: the cation, the anion, a dot, and then how many waters the salt holds around. So for every magnesium atom and for every sulfate anion, right, polyatomic ion, there's 7 waters sort of stuck around it, 7 water molecules to make Epsom salt. So that's what Epsom salt is. And we would call that magnesium sulfate heptahydrate because there's 7. Um, so yeah, so that's just a thing that sometimes you have these salts that carry with them water just because of the attraction for all that to occur, and it crystallizes nicely often is another thing. And there's usually humid, try to make these things in the winter here. So if we're calculating percent water of hydrates, this is just like we were doing. You should hopefully remember water has a mass of 18. There's 2 hydrogens, each with a mass of 1, and 1 oxygen, each with a mass of 16. So water has 18. So you're going to do this with the chart like we just did, except you're going to keep water together. So magnesium, there's 1 magnesium, there's 1 sulfur, there's 4 oxygens, and then there's 7 waters. So because there's 7 waters, we'll do 7 times 18. And then you add everything up and then do the percent of the total that was water. So of the 246, 126 grams was water, which is 51.1%. So 51.1% of Epsom salt is water. Ta-da! And that's how you do these. So for strontium chloride, there's 1 strontium. Periodic table says 87.6 grams. There's 2 chlorines. Periodic table says 35.45 grams. And then 6 waters. Each water is 18. Add those up, and the percent water would be the 108 divided by the 266.5. And then you can figure out the percent of the other ones too if you want. All right. So this is pretty straightforward, I think. Nobody seemed to be struggling too much with this part. The next part is what I want to get into. So zinc, 1 atom of zinc, 65.4 is the mass. 1 atom of sulfur, 32.1 is the mass. 4 oxygens, 16 is the mass. And then 7 waters. Each water is 18. So 7 times 18 is 126. Add all those up to get a total. The percent water is the amount of water divided by the total. So 126. So just like we were doing with percent, except now we're throwing water in as basically one of the parts of the compound. All right. So now this question. If we have sodium carbonate with some amount of water in it and we drive off the heat, what happens? What's the percent water in all this? Now, this is a lab experiment that's easier to visualize. So I want to show you a video real quick. So this is copper sulfate, and what we're doing here is sodium carbonate. So imagine, because sodium carbonate doesn't color like this, but this is basically what you're doing. So you take this blue salt, in this case, the copper sulfate. So pretend that's the other one I just said. And then you heat it up. And as you heat it up, some awful music with this. As you heat that up, going to drive off the water. And when it drives off the water, the reason why everyone uses this for the lab